NENOMATICA, where mathematics meets YouTube excellence. Let's begin with our first example. Let's solve this step by step. First, we need to understand what we're trying to find, the product of three cube root expressions. For our first step, we can rewrite this as the cube root of the product of what's inside each radical. This is possible because all three expressions have the same index. They're all cube roots. When multiplying radicals with the same index, we can use the multiplication property of radicals, which states that the product of radicals with the same index equals the radical of the products. Now, we'll multiply what's inside the radical. Let's work with the variables one by one. For the variable a, we have a to the power of 2 from the first expression, and a to the power of 1 from the second expression, giving us a to the power of 3. For b, we have b to the power of 1 from the first expression, and b to the power of 2 from the second expression, giving us b to the power of 3. For c, we have c to the power of 1 from the first expression, c to the power of 1 from the second expression, and c to the power of 1 from the third expression, giving us c to the power of 3. When multiplying expressions with the same base, we add the exponents. Now, let's rewrite this expression as the product of cube roots. We can use the property that says the nth root of a product equals the product of the nth roots. Looking at what we have inside the cube root, we can rewrite it as the product of the cube roots of a cubed, b cubed, and c cubed. Now we can simplify further using another important property. The nth root of a to the power of n equals a. Since we have the cube root of a cubed, the cube root of b cubed, and the cube root of c cubed, these simplify to a, b, and c respectively. We need to calculate the radical expression, the seventh root of a squared bc times the seventh root of a cubed b squared c to the fourth power times the seventh root of a squared b squared c squared. First, let's use a property of radicals. When we multiply radical expressions with the same index, we can multiply what's inside the radicals and keep the index the same. Next, let's multiply the expressions inside the radical. When we multiply expressions with the same base, we add the exponents. Now we can simplify by calculating these exponents. A to the 2 plus 3 plus 2 equals a to the 7th. B to the 3 plus 2 plus 2 equals b to the 7th. C to the 1 plus 4 plus 2 equals c to the 7th. For our next step, we can rewrite our expression as the seventh root of a times b times c, all raised to the 7th power. Finally, when we have an nth root of a value raised to the nth power, they cancel out. The seventh root of a value raised to the 7th power is just the value itself. Now, let's move on to our second example. We need to calculate the cube root of a minus b times the cube root of a squared plus a, b plus b squared times the cube root of the quantity a cubed minus b cubed squared. Just like in our previous example, we'll start by using the multiplication property of radicals to combine what's inside the cube roots. Now, let's recognize something important here. The expression a minus b times a squared plus a b plus b squared is actually equal to a cubed minus b cubed. This is a standard algebraic factorization. Next, we can simplify the expression by applying the product of powers rule. We have a cubed minus b cubed times the square of a cubed minus b cubed, which gives us a cubed minus b cubed to the 3rd power. Finally, we can apply the same rule as before, where the cube root of a value raised to the 3rd power is simply the value itself. So, the cube root of a cubed minus b cubed to the 3rd power is just a cubed minus b cubed. We need to evaluate the following expression. The 4th root of the quantity square root of 2 minus 1 times the 4th root of the quantity square root of 2 plus 1. For our first step, we'll use a property of radicals that states that the product of radicals with the same index can be expressed as a single radical of the product. So, we can rewrite this as the 4th root of the product of square root of 2 minus 1 and square root of 2 plus 1. For our second step, we'll apply the difference of squares formula. The product of square root of 2 minus 1 and square root of 2 plus 1 is equal to the difference of their squares. That is, square root of 2 squared minus 1 squared. In step 3, we'll simplify the expressions inside the radical. The square of the square root of 2 is simply 2, and the square of 1 is 1. So, we get the 4th root of 2 minus 1. For step 4, we'll further simplify the expression inside the radical. 2 minus 1 equals 1, so we have the fourth root of 1. For our final step, we'll simplify the fourth root of 1. Any number raised to the power of 0 equals 1, so the fourth root of 1 is 1. Therefore, our answer is 1. Let's move on to our second example. This time, we need to evaluate a more complex expression. The fifth root of x to the fourth minus x squared plus 1 times the fifth root of the quantity x squared plus 1 times x to the sixth plus 1 squared. Similar to our first example, we'll apply the property that the product of radicals with the same index can be expressed as a single radical. So, we can rewrite this as the fifth root of the product of the two expressions inside the radicals. For step 2, we need to identify what x squared plus 1 times x to the fourth minus x squared plus 1 is equal to. This multiplication gives us x to the sixth plus 1. In step 3, we combine like terms. We can write x to the sixth plus 1 times x to the sixth plus 1 squared as x to the sixth plus 1 cubed. Let's summarize what we've learned about simplifying radical expressions. When working with radical expressions, we can use properties like the product of radicals with the same index can be expressed as a single radical. We can apply algebraic formulas like the difference of squares to simplify expressions. Always simplify the expressions inside the radical as much as possible. In our first step, we need to expand the squared term on the left. Let's recall that the square of a difference can be expanded using the formula a minus b squared equals a squared minus 2ab plus b squared. Now, let's simplify the square root in the middle term. We know that the square root of 3 times the square root of 2 equals the square root of 3 times 2, which is the square root of 6. Let's combine the constant terms in the first parenthesis. 3 plus 2 equals 5. Now, we can recognize this expression as a difference of squares. We have a minus b times a plus b, which equals a squared minus b squared. Let's compute the square of each term. The square of 5 is 25. For the second term, we square 2 square root 6 to get 4 times 6, which equals 24. Finally, we calculate 25 minus 24, which gives us 1 as our final answer. Now, let's move on to our second example. Again, we start by expanding the squared term using the formula for the square of a difference. Now, we simplify the product of the square roots. The square root of 3 times the square root of 5 equals the square root of 15. Let's combine the constant terms first. 3 plus 5 equals 8. Now we can see that we have negative 2 square root 15 plus 2 square root 15. These terms cancel each other out. Welcome to our math video. Today we'll solve a complex expression step by step. Let's look at the problem. We need to evaluate the following expression, the square of the quantity square root of 3 minus square root of 7, multiplied by the quantity 10 minus 2 times the square root of 21, multiplied by the square of the quantity 10 plus 2 times the square root of 21. Let's start by evaluating the first part of the expression, which is square root of 3 minus square root of 7 squared. To square a binomial, we can use the formula of minus b squared equals a squared plus b squared minus 2 times a times b. Substituting our values, we get 3 minus 2 times square root of 3 times square root of 7 plus 7. This simplifies to 3 minus 2 times square root of 3 times 7 plus 7. Now we can simplify this to 3 minus 2 times square root of 21 plus 7, which equals 10 minus 2 times square root of 21. After evaluating the first part, our expression becomes 10 minus 2 times square root of 21 multiplied by 10 minus 2 times square root of 21 multiplied by the square of 10 plus 2 times square root of 21. We can see that the first two factors are identical. So we can rewrite this as 10 minus 2 times square root of 21 squared multiplied by 10 plus 2 times square root of 21 squared. Now, let's focus on this pattern. We have a quantity squared multiplied by another quantity squared. Let's group them together to see a clearer pattern. Looking at the expression inside the brackets, we can see that it follows the pattern of minus b times a plus b, which equals a squared minus b squared. In our case, a equals 10, and b equals 2 times square root of 21. Therefore, 10 minus 2 times square root of 21 multiplied by 10 plus 2 times square root of 21 equals 10 squared minus the square of 2 times square root of 21. This gives us 100 minus 4 times 21, which equals 100 minus 84. So we have 100 minus 84, which equals 16. And finally, 16 squared equals 256. Welcome to our math lesson today. We're going to explore an important property of square roots, and when it's reversed doesn't hold true. Let's start by recalling a fundamental property of square roots. For any non-negative real numbers, a and b, the square root of a times the square root of b equals the square root of a times b. This can be written mathematically as the square root of a times the square root of b equals the square root of ab. This property is always true for non-negative real numbers and is widely used in algebra and calculus. Now, let's consider the reverse of this property. Is it always true that the square root of a b equals the square root of a times the square root of b? Mathematically, we're asking if this equality always holds. The square root of a b equals the square root of a times the square root of b. The answer is no. This reverse property is not always true. Let's see why. Let's demonstrate this with a concrete counterexample. Consider a equals -2 and b equals -3. Let's substitute these values into both sides of the equation and see what happens. For the left side, we have the square root of -2 times -3, which is the square root of 6. For the right side, we have the square root of -2 times the square root of -3. But here's the problem. The square root of -2 and the square root of -3 are not real numbers. The square roots of negative numbers are complex numbers, so the expression on the right is not equal to the square root of 6. Welcome to our lesson on verifying radical equations. Today, we'll examine two equalities involving radicals and work through each step to verify whether they are true. Let's start with our first example. We need to verify whether the radical equality square root of 300 equals 10 times square root of 3 is true. To verify this equality, we'll manipulate the left side to match the form on the right side. Our first step is to write the square root of 300. This is the starting point of our verification process. Next, let's break down 300 as a product. We know that 300 equals 100 times 3. So we can rewrite the square root of 300 as the square root of 100 times 3. Now, we can use the product property of square roots, which states that the square root of a product equals the product of the square roots. So the square root of 100 times 3 equals the square root of 100 times the square root of 3. Finally, we know that the square root of 100 is 10. So our expression becomes 10 times the square root of 3. Looking at our original equality, we started with the square root of 300 on the left side, and through our algebraic manipulations, we arrived at 10 times the square root of 3, which is exactly what we have on the right side. Therefore, the equality square root of 300 equals 10 times square root of 3 is true. Now, let's move on to our second example. We need to verify whether the radical equality the fourth root of 243 equals 3 times the fourth root of 3 is true. Just like before, we'll start with the left side of the equation. We begin with the fourth root of 243. Let's break down 243 as a product of factors. We can write 243 as 81 times 3. Next, using the product property of radicals, which applies to any root, not just square roots, we can rewrite this as the fourth root of 81 times the fourth root of 3. Now, we need to recognize that 81 can be expressed as 3 raised to the fourth power. So, the fourth root of 81 is equivalent to the fourth root of 3 to the fourth power. When we have the nth root of a value raised to the nth power, the result is simply the value itself. So, the fourth root of 3 to the fourth power equals 3. Our expression becomes 3 times the fourth root of 3. Looking at our original equality, we started with the fourth root of 243 on the left side, and through our algebraic manipulations, we arrived at 3 times the fourth root of 3, which matches exactly what we have on the right side. Therefore, the equality fourth root of 243 equals 3 times the fourth root of 3 is true. Welcome to this tutorial on simplifying radical expressions. In this video, we'll learn how to work with expressions involving roots and powers to simplify them step by step. Let's start with our first example. We need to calculate the cube root of the quantity a plus b raised to the power of 4. When simplifying radical expressions, we need to understand the properties of exponents and roots. Let's apply these step by step. Now, we'll separate the cube root into the cube root of each factor. This allows us to simplify the first term, since the cube root of a quantity cubed equals the quantity itself. The cube root of a quantity cubed equals the quantity itself. This simplifies our first term. And we've arrived at our final simplified form. The cube root of a plus b to the fourth power equals a plus b times the cube root of a plus b. Let's move to our second example. We need to simplify the fifth root of a to the seventh power times b to the sixth power times c to the 10th power. We'll approach this by separating the powers into combinations that will work well with our fifth root. Now we'll group the powers that work well with the fifth root, and then separate the fifth root. Now we can simplify the first part of our expression. The fifth root of any quantity to the fifth power equals that quantity. And we've now arrived at our final simplified form, which is a times b times c squared times the fifth root of a square times b. Let's examine our final example. We need to simplify the 70th root of x to the 74th power times y to the 75th power. Let's rewrite this as powers that work well with the 70th root. We can split this into x to the 70th power times x to the fourth power times y to the 70th power times y to the fifth power. Now we'll separate the 70th root of each term using the property that the root of a product equals the product of the roots. The 70th root of x to the 70th power equals x, and the 70th root of y to the 70th power equals y. This simplifies our expression. Our final answer is x times y times the 70th root of x to the fourth power times y to the fifth power. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.